Hello everybody, and welcome back to another Eng 130 video tutorial. In this tutorial, we're going to continue on with shear and bending moment diagrams, but instead of finding equations by cutting the beam like we did in the previous video, we're going to use what we know of the relationship between load, moment, and shear to try and figure out the bending and shear moment diagrams in, I'm air quoting this loosely, an easier way, and that is through just direct relationships. So there's relationships, as you'll see, between moment and shear diagrams, and if you know the load, then you can find the shear diagram, and if you know the shear diagram, you can find the moment diagram. So that's what we're going to do here, and in this example, we're going to keep it very simple, and we're only going to deal with point loads and point moments, or concentrated moments, or as some people even call it, moment couples. So this is kind of the first step. And then the next example, we're going to get a little bit more complex when we have a constant distributed load. And then we're going to wrap it up by going with a linear distributed load, which can be the absolute worst case scenario. So with that being said, let's get started. So looking at this example, it's pretty straightforward. It just wants us to draw the shear and moment diagrams for the beam. And that's basically what your final exam question is going to be. It's going to be that simple with a little bit more tricks involved. But this example won't contain the tricks. I'll talk about the tricks in later videos, especially the next two videos. Those will be the ones that we discuss kind of the tricks of what they can do. But for this video, we just want to draw the bending and shear moment diagram for this nice, simple beam. So before I start talking about the relationships between shear and moment, the first thing that you guys will always need to do in these type of questions when you want to draw the shear and bending moment diagram is to find the support reactions, because those are actually going to be very, very critical to determining the bending and shear moment diagram. So in order to determine support reactions, we're going to, of course, have to draw the free body diagram of the beam. So I'm going to draw a little beam like this. Hopefully it's not too bad. All right, so here's my beam. I'm going to draw a support reaction. So I know what A, it's a pin. So that's going to be AX and AY. And what you guys will find is the majority of the time in these type of problems, AX will be 0, because beams, well, they're really used for supporting gravity loads, so loads that go downward or vertical. So it's very rare that we see a beam with a normal force in it. So we got AX, AY, and now we got BY. So next I better just label them before we all get confused. So AX, and we got AY. And as for point loads, we got two concentrated loads 1 meter away from each support. So I'm going to put those in. So those will go like this, and I'll label the magnitude of each one. So we got 800 newtons and 600 newtons. So 600 newtons, 800 newtons. And finally, right at the center of the beam, we have a concentrated moment, which I'll put like this, and we know that this is 1200 newton meters. 1200 newton meters. And of course, it's not a free body diagram unless we throw in all the dimensions. So the distances is pretty nice. It's all segmented at 1 meter. So we're going to have 1 meter, 1 meter, 1 meter, 1 meter, and that's it. So we know a variety of ways to determine the support reactions. We can start with some of the force in X. We can take a moment about any point. For me, I'm going to start with some of the moments in the X direction, or some of the moments, some of the forces in the X direction is equal to 0, because right away we can tell and conclude that AX is equal to 0. So again, it's very, very trivial for these type of questions, but it's very important to try and figure it out and make sure. So for the pin, I always like to take the moment about it because it gets right to my reaction. So if I take some of the moments about A is equal to 0, I'm going to get a nice long equation because there's a lot going on in this beam, and we got 800 newtons. So I'm going to put 800, and it acts at a distance of 1 meter. And we know that this is going to cause a clockwise rotation about A. So it's going to be negative. Moving on, we got a concentrated moment of 1200. So we're definitely going to have 1200 in here. And the rotation of that moment, as you guys can just see, is clockwise. So it'll also be negative. And then moving on, we got the 600. And it'll be the same rotation as the 800. So it's going to be minus 600. But this distance is now 3 meters. And finally, at the far end of the beam, we got BY, but this one's the only one that creates a counterclockwise rotation. So it's plus BY, and the distance is 4 meters. And of course, it's all in equilibrium, so therefore everything must equal 0. So in the end, we can just do simple algebra, and what we'll do is we'll find that By is equal to 950 newtons. And this is kind of a little bit funny because when we go through and solve the bending and shear moment diagram, we won't use By whatsoever. Well, we'll kind of use By, but I'll show you guys why we calculate By. It's not critical to this finding the bending and shear moment diagram, but as you guys will see, By will be a check for you guys to make sure that your diagrams are actually correct. All right, so we're going to finish up with sum of the forces in Y is equal to 0, because from that, we have AY going upwards, and we have minus 800 minus the 600. So minus 800 minus 600. And then we got a BY going upwards at 950. So plus 950. And this is all equal to 0. So solving for this, I can solve for AY. And we find that AY is equal to 450 newtons. And I'm just going to put real quick that both AY and BY are going upwards. So that's the first step, is to solve for the support reactions. And like before, I'm just going to highlight them so that when I look back, I know exactly what they are, because again, these aren't the final answers, but they're going to be very, very important in figuring out the final answer, which is, of course, the diagram. So I got AY, I got BY. So now what you guys are going to have to do, mainly for the lab and for assignments and stuff like that, is you guys are going to have to start drawing the template of the diagram. And the template of the diagram is very, very nice because it should be very organized and tell us exactly what you're doing at what points. Now, the diagram template is usually actually given to you in the exam. So, but for us, we're going to have to draw it manually because all I got is this paper. So what's going to happen is the first thing that you guys are going to want to do is draw the beam. So we're going to go over here. We're going to go 1, 2, 3, 4 meters across. So I'm drawing the exact same beam I did before. So nothing's changing about this beam. But now I'm going to put all of my loads on it, and all the loads as actual numbers. I'm not going to put AY or BY, I'm going to put the actual loads. So starting with AY on this side, I know I got AY acting upwards, and it has a magnitude of 450 newtons. On the far side, I got BY acting upwards, and I know that BY has a magnitude of 950 newtons. Going across the beam, I got an 800 and a 600 Newton force downwards. So from here and right here, like this. So I'm just going to put this in right here. So on the right-hand side, we got 600 newtons. On the other side, we got 800 newtons. And then at the center, we have a concentrated moment. And this one is 1200 Newton meters. Alrighty, so there's my beam, and all the loads are on it. As you guys will see, all the loads are on the beam, so there should be no confusion of any unknowns. Next, I'm going to dimension the beam and put its span. So across here, we know that all those segments are just going to be 1 meter long. So 1 meter, 1 meter, 1 meter. And next, I'm going to draw a big, long line, and this is going to be kind of the y-axis of all of our diagrams. So I'm going to draw a big line all the way down. And what I'm going to do is I'm going to draw more vertical lines every time there's a load change. And so if I look here, well, at x equals 1 meter, I have a point load. So let's draw a line down there. There's a concentrated moment. Let's draw a line over here. And then just kind of go all the way through. And what you guys will see is you're going to draw a line for every dimension that you did in your dimension. So I segmented this into 4 parts. My graph should have 4 parts. So moving down, this is going to be my kind of the y-axis. Oops, the y-axis for my bending and shear moment diagram. So now I'm going to have to add an x-axis for all of them too. So if I look over here, I'm going to say, okay, well this will be my x-axis for the shear. So I'm just going to put x, and we know that x will have units in meters. So this will be when my shear is equal to 0. And if I come down here some more, I'm going to draw a second one, which I'll put over here, like this. And this will be my x-axis for when the moment is equal to 0. So right here, I'm just going to put 0, and I'm going to label these 2 diagrams. So the first one is going to be my shear. So I'm just going to put shear. And this will have units of newtons. And then at the bottom, I'm going to have moment. and this has units of Newton meters. So I'm just going to kind of erase the 0 down here, and I'm going to put 0. So I'm going to draw my diagrams just right here. And again, all these axes here, like this kind of profile, this is typically given to you in an exam. You won't have to draw it, or else you'll just be wasting a lot of time. But what I'm going to do is I'm going to draw my diagrams here, and any calculations that I do, I'm going to put down here. So right here, I'm just going to go calculations. But before I do calculations, I just want to show you guys the theory. And I'm not going to go into any calculus or anything like that. I know you guys want me to, but of course I'm not going to do that. And I'm just going to show you what each load in this scenario. So I'm not going to cover distributed loads. That'll be next class, or next video. I'm getting you guys mixed up with the class now. So I'm just going to show you guys the effects of point loads. So point loads in a shear and bending moment diagram, they jump the shear diagram. They jump the shear diagram. And I know that sounds really confusing, shear diagram. I just about wrote the word confusing. But what it means is if I have, let's just say, a segment of a beam. So I'm not going to draw any segment, but at this part of the beam, I'm going to have a load. And the load here goes, actually I'm going to draw two loads just to show you guys exactly what I mean. So if I had two loads on this beam, so I had a load going down, and let's say over here I have a load coming up. Let's say the load on the left is P and the other one is F. What happens in my diagram, my shear diagram, is let's say that it's coming over to here, and what happens is at point P, so I'm just going to draw dots all the way down. So dots. What's going to happen is my shear diagram is going to drop by a magnitude of P. And then between P and F, nothing happens. So my diagram is going to remain flat. Oops, that was terrible. So hopefully this one works out better. Not really. All right, so let's erase this and let's try and make this a little bit cleaner. So what's going to happen at this point is going to drop down by a magnitude of P. Between P and F, nothing happens, so it's just going to go straight across. And then at the end, it's going to jump up by a factor of F, and then it's going to carry on. So I'm just going to put real quick over on the side here that this is the shear, so you guys can see what's going on. So if I have a point load going downwards on my shear diagram, it's going to drop down by whatever magnitude that is. If I have a load going upwards, it's going to pop the load up by a factor of whatever it is. So right here, I guess I should label these. So this right here, this is magnitude of P, and this right here is magnitude F. And what we can do is, using this, we can actually find our shear diagram for this beam right here. So let's draw it in purple. If I look at the very left, and this is what you guys are always going to want to do, is you guys are want to look left and then slowly make your way to the right. The shear is going to start at 0, and then if we look, we have a point load right at the left side of 450. So if we look down here, we see a point load jumps up or jumps down our shear diagram. And we see this one goes up. So our diagram is going to jump up by a factor of 450. So it's going to go up to here. And we know that this value is going to be 450. What I also said is if there's nothing between those point loads, the shear just stays constant. Then that makes sense. So if we look over here, over the span of the 1 meter, so from 450 to 800, nothing happens. So this is going to come straight across like this. But now we find something interesting is we have another point load of 800, and this point load goes downwards. So this point load is going to now jump our shear diagram downwards by a factor of 800. So if I come down here, it's going to come somewhere to here, and this value is going to be negative 350. That makes sense because we go from 400 and we go 800 downwards, we're going to end up at negative 450. So looking at the beam for the next span of 1 meter between the 800 newtons and the 1200 newton meters, nothing happens to the shear. So there's no loads, no nothing, so we know our shear is just going to be constant. And if we look a little further, well actually now is at the point where we have a concentrated moment. what you guys will see is the moment will do nothing to our shear diagram. So I'm going to put the little star here. Concentrated moment. Does not affect shear diagram, or it does not jump. Shear diagram. And I know you guys are wondering, well, what do you mean it doesn't jump shear diagram? And why not affect it? And I took out the word affect because it actually does affect it somewhat, but it affects it indirectly. And this comes with this over here. So if I'm going to highlight this in green, when I'm doing sum of the moments at A is equal to 0, I have to include the 1200. And because of that 1200 changes my BY down here. So if I didn't have a concentrated moment, BY would change, which then AY would change, and then this first jump right here, that would change. So it indirectly affects the shear. But when we're doing these kind of quick and easy methods, we don't need to worry about concentrated moments in the shear diagram. So what does that mean for us? Well, it means that instead of just going constant for 1 meter, the shear is actually going to go, stay the same all the way until the next point load. And if we look at the next point load, it's 600. So we know that we're going to have to drop down yet again by a factor of 600. So down here, negative 350 minus 600, that gives us negative 950. And of course nothing happens, so we're going to pop out to the end. So something like this. But now this is kind of what's interesting, is if we look at a beam, at the end of a beam the shear must be 0. It must be 0, kind of all the time, unless, well, actually no, it'll always end up at 0. So that's kind of a little hint to you guys. The shear will always end up at 0. So not even looking at BY, I know that to get from where I'm at now to 0, I need a vertical load upwards of 950. And if I look up here, and I'm going to highlight this, I see that my BY is 950. So what could have happened is I could have not calculated BY, because I know that my shear must go to 0. But now that I know BY is 950, and I know that my jump needs to be 950, it acts as kind of sort of a proof that says, okay, I'm actually correct, which is great. That's what we want. So actually, I won't do that. So the final thing I like to do for these diagrams is just kind of shade them in a bit, and it'll help you guys kind of for the next part, which is going to be moments. So moments are kind of funny because we're going to need to use the shear diagram to solve for the moments. I don't know, there's something satisfying about watching all these lines become straight. But yeah, so for shear, it's very, very easy. We just look at the point loads, and as you'll see, we'll also look at the distributed loads, and we'll do that in the next video. But for right now, it was very easy. We just, every time there was a point load, we make a jump, and that's it. But for moments, it's a little bit different. So for moments, or moment diagram, I know this is theory of everything. It's not really making much sense. So moments, the change in moment, so change in moment about 2 points is equal to the area. So this is going to be, I'm going to put this in a different color because this is very important. The area under the shear diagram. And this is going to be the most important thing that you guys learn. And I'm not kidding, because this will save you guys a lot of time. So if I came down here, and let's say that for my shear diagram, so I'm just going to make kind of a crappy shear diagram. So let's say that my shear is something like this between these 2 points. So the shear goes from 0 to, let's just say 20, between x equals 0 and x equals 2. Well, I should put this as shear. Well, that means that if I'm doing my moment diagram down here, and I want to find the change in moment between 0 and 2, and we know that the moment starts at 0, to find the point at 2, all I'm going to do is say that my delta m, and I'm just going to go from 0 to 2. So from x equals 0 to x equals 2 is equal to the area under my shear diagram. So it's going to be equal to this area. So if I look at my shear diagram, the area is going to be 20 times 2, which is equal to 40. So what that means is that at x equals 2 on my moment diagram, my moment is going to be 40. So it's going to be 40. And the next thing that you guys need to know is and I'll write these down, but it's easily proved later, and I'll prove it more. Well, it's actually kind of proved in the last video, but I'll prove it more later on, is that constant shear is equal to a linear moment. So if we look up here, I see that my shear between these two sections is constant. It stays at 20 the whole time. That means my moment diagram is going to be linear between these 2 points. So this will be my moment diagram right here. Okay, well, let's actually see some examples. So let's go over here. If I'm doing the moment diagram based on the shear diagram, so I'll do this in purple as well, I know my moment's going to start at 0. The moment's always going to start at 0. It's going to end at 0. So my moment's going to start at 0. And if I look, I have no concentrated moments. So between delta m, so delta m, I'll do it down here. So for the diagram, so my change in moment between x equals 0 and x equals 1 is going to be the area under the shear diagram, the area under the shear diagram between those two points. So I want this area right here. So we know that it's going to be 450 times 1 meter. So right here, my change in moment is going to be 450 times 1 meter, which is equal to 450. So I can come up right up here to my my moment diagram, and I know that it's going to jump up to right here, which is, we're going to say 450. And since the shear is constant, we know that this is going to be linear up to this point. So I'm just going to erase this highlighting. Okay, perfect. We're good to go. So now if I go to the next span, my delta m, oops, I zoomed in too much, sorry. My delta m between x equals 1 and x equals 2 is again going to be the area under that shear diagram. So if I look up, it's going to be this area right here. So we know that that value is negative 450 times 1 meter, or negative 350. So we're going to have negative 350 times 1 meter. So it's equal to negative 350. So if I come up here to my moment diagram, if I'm at 450 and my change there is negative 350, I know that my point's going to end up down here at 100. So this is going to come down like this. It's going to be linear. So now something special happens. And this is the thing that's going to cause a lot of students the most problems right here. And it's that concentrated moment. Now, concentrated moments act the exact same way as concentrated loads, except there's one trick. And this one trick is what confuses absolutely everybody. And that's this. If we look at this moment, so I'm going to highlight it so everyone knows exactly what I'm talking about. If we look at that moment there, it's a negative moment. It's clockwise, it's a negative moment. And if we look at loads, so if we look at this load over here, or actually that's probably not the best one. If we looked at the 800 right here, a negative load dropped my diagram. Makes sense. I have a load going downwards, it's going to drop it downwards. If I had a load going upwards like the 450, a positive load, it pops my diagram up. Now, this is where it's going to get tricky. If I have a negative moment, which is, oops, I deleted too much. If I have a negative moment, which is what I have in this case, I have a negative moment, this is actually going to bring my diagram up. And I'll just go to here. So a negative moment brings the diagram up, and a positive moment brings the diagram down. And that just has to do with the sign convention that we defined. So the magnitude it jumps up is going to be 1200. So if I started at 100 and I add 1200, I'm going to end up at 1300 newtons per meter. So we're going to go up, and then, okay, perfect. So now we're at 13. So now in order to find the next point of the moment, all we have to do is find the area under the shear diagram, between the next section, which is going to be this section right here. But we see that this section is the exact same as the last section. So delta M, 2 to 3, is going to be equal to negative 350 because the shear doesn't change. So we know that we're going to pop down, where am I? We're going to pop down from 1300 to 950. Pop down like this. And I'm going to put that 950 a little bit lower so everyone knows exactly where that is. And then finally, for our last area, which is going to be, where's my highlighter? This over here, the shear does change, so we're going to have to recalculate it. And we see that the magnitude of the shear there is 950 times 1. So our delta M between 3 and 4 is going to be equal to negative 950 times 1, which is negative 950. So if we go up here to our diagram and we're at 950 and we minus 950, we know that our moment must end up at 0. So something like this. So this right here is going to be our moment diagram. So I'm just going to kind of fill it in, make it look nice and pretty. And as you guys can see, of course, I dragged this out a long time. It's not usually taking this long. If I were doing this, it'd probably take a couple minutes. But we can figure out the shear and bending moment diagrams really, really fast by using these relationships, knowing where things jump, knowing when things jump down or jump up, stuff like this. So that's my bending and shear moment diagram for this beam. And this is showing you guys what to do with point loads. Now, things change a little bit when we get to distributed loads, and I'm going to show you guys that in the next video. And what's going to happen is two things. The first thing is if we have a constant distributed load, so nothing linear, it's just a constant distributed load, things are actually still pretty nice. And we'll be able to solve absolutely everything using kind of the same methodology we are now, just relationships. Now, if the the distributed load is linear, that's the absolute worst case scenario you guys can get. Because what's going to happen is you guys are going to need to find equations. Now, I know all you guys might get a little scared when I say that because, well, equations suck. As you guys saw from the last video, no one wants to find equations. They're always terrible to find, but there's actually a little secret method to find those equations. And I'm going to show you guys that secret method to hopefully save you guys a lot of time on your final. So, I think that concludes this video. I'll see you guys in the next video when we cover distributed loads. Thank you guys all so much for listening, and I'll see you next time.